Okay, today's lesson is about using Newton's second law. Um, but before we get there, I'm going to backtrack and tell you what you should have seen in the lab. So, spoiler alert, if you want the lab to be completely novel to you, make sure you're done the lab before you watch this. Or flipping it, if you're struggling with the lab, then this will kind of tell you what the outcome of the lab, what you should have seen, what hopefully you handed in. Um, I'll talk you through kind of the outcomes. I'm not going to switch back and forth to the simulation, but I'll show you what you should have got. So we'll get that out of the way for now. Part one of the lab was actually the more complicated one. What you had to do in part one is use that simulation and set the force to something. So I played around with it and I set the force to 20 newtons and I just left it there. Then what you did in the lab is you chose a particular mass, you ran the simulation based off of 2 points, you found the acceleration, and then you were instructed to find the inverse of your acceleration. That's what made it weird. Part one, you had to do this 1 over a thing. I've simplified my chart a little bit. You had to use data points, but this is kind of the outcome of part one. When I did it, when I picked 1 kilogram and I ran it with a force of 20, I got an acceleration of exactly 20. Then on my calculator, I did 1 divided by 20. Literally, I punched that in and I got a decimal value of 0.05. Then I did it again. I switched the mass to 2 kilograms. I ran the simulation. I got 2 points. From the points, I got the slope, which is my acceleration value, and this time I got it to be 10. I didn't need my calculator, but really 1 divided by 10, that's what we're going to put in the third column. 1 over 10 is the same as 0.1. Then I did it a third time, and my third time I chose 3 kilograms. When I got my 2 points and found the acceleration was a bit of an uglier number. It was 6.67. Then this time I had to use my calculator again. When I did the inverse of 6.67, I had to round it off, but I rounded off to, sorry, to 0.15. You should probably get more than 3, but that's kind of what I got when I did the lab. Then, how come my thing won't let me zoom? There we go. Then you were asked to graph it. And specifically, you're asked to graph and put m on the vertical and 1 over a on the horizontal. So these are going to be my m numbers, and these are going to be my 1 over a numbers. Hopefully you did it with Desmos or Google Sheets or something, but I'm just going to roughly draw it on here. My points are in my chart. My first point was go over, this is related to my x, go over 0.015 and go up 1. So over 0.015 and then go up 1. So this was a point on my graph. Let me get myself in the frame and get rid of that for now. My second point was over 0.1 and up 2. Over 0.1, if we're drawing it to scale, is twice as far, so it would be over twice as far, and 2 would be up twice as high. Obviously, you don't have to make your graph colorful. I'm just trying to make it easier for you to see. My third point, I go over the 1 over a, which this time is 0.15, and up 3. So 0.15, nice and evenly spaced, should be right here. And then 3, if I draw this well, evenly spaced, should be up here. So that is what the graph should look like for part one. I usually do an XY scatter and get a trend line, but you could have done a linear graph. It looks like when we connect those dots, this worked out pretty good. Yeah, it kind of looks like that. And it looks like it's going through the origin. I can't exactly remember how I typed the lab, but the next step is to look at that graph and try and come up with an equation. To get the equation, we kind of got to do two things. We need to know the slope. Slope is always rise over run. Sometimes in math class, your teacher would draw like a little triangle kind of in the corner. So we're like going to go, here's my run, here's my rise. It's nice and linear, so it shouldn't be too tricky to find the slope. If I use that, it went through the origin and it went up to 2. 2 is my rise. and the run was 0.1. That's my slope. My slope is 2 divided by 0.1, which is 20. Yeah, that's kind of familiar. 20 is what my force was at the beginning of all this. That was one of the questions in the lab as well. Okay, the really cool step, and we'll do this over and over again in physics, get data, graph the data. When the data is linear, we can use just common grade 8, grade 9 math to figure out the equation. We know that for a straight line, the standard form is y equals mx plus b. In this case, when we graphed it, instead of y, we put the mass on the side. So I'm going to put the letter m for mass to replace the y, because that's what we graphed. There's too many m's, so instead of writing mx, I'm going to write the word slope, just so I don't get my m's confused. And then on the x-axis, we had 1 over a. So instead of x, I can replace x with 1 over a. And in this particular one, it went through the origin, so my b value is 0. So really my equation that matches this data is mass equals slope times 1 over a. And then one little logic leap, the slope was 20, which is the exact same as the force. So if I do that little substitution, I can say that, oops, didn't mean to jump zoom. I can say that mass is equal to force times 1 over a. It's a little bit ugly, but that's the relationship we got from this part of the lab. We've connected the mass, force, and acceleration in this weird equation that mass equals force times 1 over a. That's part 1 of the lab. I'm going to give you another talk through on part 2 of the lab. Part 2 of the lab, actually, I found a little bit easier because we didn't have to do that weird 1 over. In part 2 of the lab, again, you've got to figure out the simulation, but you're asked to pick a mass. When I played around, I set the mass to 2 kilograms. Then you set the force and figured out the acceleration that went with it. In the lab, you had to find 2 points, then use the 2 points to find the slope. I'm just going to skip that step. When I ran it, when I had a force of 10 and I got my 2 points and I found the slope, that worked out to a slope of 5, which means the acceleration was 5. Then I bumped it up to a force of 20, and my acceleration also jumped up to 10. Then I changed it to a force of 30, and my acceleration jumped up to 15. You could have gotten more. I'm just going to pause at 3. Then the instructions in the lab were to graph it. Specifically, put A on the x-axis and force, oops, that A is going to be in the way again, and put force on the y-axis. So using my data points, one of my points was a force of 10 with an acceleration of 5. So that means go over 5, up 10. So there's a data point. My other point was a force of 20 with an acceleration of 10. So go over 10, up 20. Being a little bit messy, but it's kind of like the last graph, nice and linear. The last point was 15, 30. So over 15, up to wherever 30 is. I was a little bit more messy with this one, but when I connect that with a straight line, again, it should be through the origin and looks kind of like that. We can use a linear graph to get an equation. We need to find the slope, so I might as well do that first. Based on this data, I'm going to go with that second point again, do that cool triangle thing. My run was 10. With a run of 10, my rise was 20. So I can say my slope is a rise of 20 over a run of 10. So my slope equals 2. And hey, that looks familiar. That's the mass that I used. Now, we got the slope. The next part is do a little y equals mx plus b. Instead of y on the vertical axis, I have the letter f. So I can literally replace y with f. It's mx. That m in the mx is the slope, and we've got m for mass, so I don't want to get confused, so I'm going to replace that with the word slope. We have to multiply that by x. X in this case was the acceleration, so instead of x, I'm going to write the letter a for acceleration, and the b value was 0. From our slope calculation, I observed that the slope was 2, which is the same as the mass, so I can say that slope is the same as mass. Mass we can call letter m, so F equals m for mass, which is the same as a slope, which ironically gets given the math short form of m anyway, so a whole bunch of m's in here. Hopefully it's not too confusing. Multiplied by a. I don't need to put the plus 0. That's the more common way to write it, but that's Newton's second law. F equals ma. In the questions we're going to do today, we'll bring in friction and forwards and backwards forces, so we'll write it as F net equals ma. But that's the outcome to the lab. That's what Newton's second law is. Newton's second law, we call it F net because sometimes there's friction and other forces to consider. But F net equals ma. Really, the F net is, think back to Newton's first law, it's the amount of unbalance. When there's, from Newton's first law, if you have an unbalanced force, then the motion is going to change or the object's going to accelerate. So from Newton's first law, an unbalanced force or an F net creates an acceleration. Newton's second law is the math on it. If there's an unbalance, if there's an F net, we can figure out the acceleration using F net equals m times a. Really what this does is it kind of defines what a kilogram is. Mass, or the number of kilograms something is, really tells you the amount of inertia something has. Something that's really, really heavy with a big mass, it would take a big force to make it accelerate. If you had something that's light, less mass, less inertia, a smaller force would make it accelerate. So hopefully that helps with the lab. The lab is a little bit confusing, especially part 1 where you have to do that weird 1 over thing, but this is the outcome that hopefully you can get, or hopefully you did get. For part 1, the mass is related to the inverse of the acceleration. The connector is the force. We can say m equals F times 1 over a. I'll add one little bit here. If we multiply both sides by a, we get m times a on the left equals F on the right, which is just mathematically equivalent to what we get in part 2. All right, I think that's enough talking for me on the lab. Again, hopefully it clicked. If it didn't click, email, ask for help, take your time going through it. And then the next part of today's lesson is to actually use this equation, F equals ma. If I give you a force, you should be able to use it to calculate the acceleration. Or if I give you an acceleration, you could use the equation to figure out what force made that acceleration happen.